Hello, welcome to the section for this week. Here I'm going to be talking about change of variables, both in 2 dimensions and in 3 dimensions, and talking a little bit about some of the sort of most usual change of variables, situations that we do polar, spherical, and cylindrical coordinates. So to begin with, we're just going to talk about the situation in 2 dimensions first. So here we've got an integral that we're attempting to perform, that we're interested in terms of x and y over some region D of the scalar valued function small f, dependent on x and y. And in order to accomplish it, we think about this other region, D star, and some function capital F that maps from D star onto the original region D in this particularly nice fashion. It's essentially a one-to-one map, so it's sending each coordinate uv to a unique xy. It's a C1 function, so it's got a first derivative matrix, and we ensure that it's essentially an onto function covering all of D. And there's a little bit of room here for these conditions to fail sort of on small low-dimensional sets, which comes up especially for things like polar or spherical coordinates where we're talking about angles and we've got this periodic behavior where, the angle 0 and 2 pi agree. And so we've got this thing that looks like that these two endpoints, these two things are being mapped to one location, but because it's on a small dimensional set, it doesn't matter. And then the formula that we use to take advantage of this mapping is to do our integral in terms of the new coordinate, in terms of the coordinates u and v that are sort of the ones as written before applying this mapping. We evaluate our function, in terms of them, and we multiply by this additional factor that's the absolute value of the determinant of the derivative matrix of our function. And perform this integral against the element du dv. And so this absolute value of derivative of df, also sometimes written as the absolute value of the sort of partial of the vector xy over the vector uv, is giving us the sort of scaling by which the area changes locally near the coordinates uv. Alright, so to do a problem related to this, we can think about this, where we've got a region that we're interested in that's bounded by these curves. And so I'll draw in xy, we're bounded by the curves e to the x and e to the x minus 1, as well as 1 minus x squared and 4 minus x squared, which is giving us this sort of deformed square in the middle. And we want to integrate over this region this function e to the x plus 2x, depends explicitly only on x. And here we want to use this these new coordinates that are sort of suggested by our bounds, y minus e to the x, and y plus x squared, and sort of this might be a good idea because our bounds are then s equals 0 and s equals 1, or sorry, s equals negative 1, negative 1 to 0, and y is from 1, or sorry, t is from 1 to 4. Goodness, I'm talking about them backwards. Yeah, our bounds are s from negative 1 to 0 and t from 1 to 4. And we want to first figure out what this region we would want to be performing the integral in, based on these new bounds, and because they're horizontal, it's going to give us this sort of rectangular region. Or because our new boundaries are constants, it's going to give us this sort of rectangular region. Here we've got this situation where it's different than the framework exactly presented in the theorem from the notes, where instead of having our coordinates x and y that we're interested in naturally from the integral as it was given to us, expressed in terms of our new parameters, we've got them written the other way around. The s and t are given to us in terms of x and y, and it's going to be it would be very difficult to compute what y and what x are in terms of s and t given the way that they're given to us. But we can take advantage of this this fact that the derivative of an inverse function is given by the inverse matrix of the derivative. And so we can compute first the derivative matrix of the transformation that's taking us from xy to st, that's sort of as the transformation has been written, and then just take the inverse, consider the inverse matrix of that, and use the fact that the determinant of an inverse matrix is just 1 over the determinant, that we can do all of our computation sort of the way it had been written, and then just take a reciprocal there. And so to do this, we can say that this function, or I won't write it as f because it'll get confusing whether I mean f as in the theorem or as written here. But we can think about the matrix of partial derivatives that we're interested in. That's going to give us first the derivative of s with respect to x and the derivative of s with respect to y on the first row, and then the partials of t with respect to x and with respect to y on the second row. And here we've got s is given by minus e to the x and a 1 in y. T is given by a 2x and a 1 in y. And so if we take the absolute value of the determinant of this, I haven't left myself too much space, have I? I'll call this df inverse after all, as in the notes. So the determinant of df inverse that we're after is going to be an absolute value. So we're going to get a minus e to the x minus 2x, and so in absolute value that's going to give us e to the x plus 2x, which is telling us that the one we want, the absolute value of the determinant of the change of variable matrix that's going from st coordinates to xy coordinates, if we were to be able to compute what that function is, which we won't write down explicitly, we're going to get that is 1 over e to the x plus 2x. Now, what we would want is for this to be written in terms of s and t, and if we were able to figure out what x was in terms of s and t, we'd be able to write this the way we wanted it, so that ultimately we could do this integral in terms of s and t, where those are our only variables. Here, that's going to be very difficult, but we can, if we write out the whole integral that we're trying to compute first, we can see that it's not actually going to be necessary for us to figure out what this looks like explicitly in terms of s and t, because our integral, as in the theorem, our integral over the region D originally of e to the x plus 2x, if we were to do it dx dy or dy dx, is going to be the integral over the region D star, which I we can put in the bounds. It's going to be the integral. We'll settle the bounds in a second. We'll do the integral of d star of e to the x plus 2x, our function that we would want to find in terms of s and t, but we don't know how, times our area element, absolute value determinant df, which was 1 over that, and then ds and dt. And so what we see is that we really get, let me make that a little bit smaller. Is that we're really getting a cancellation here, where we've got these two reciprocal things, they're going to cancel out to 1, and so we're just going to talk about the integral where s and t are ranging between their bounds of just 1. And so here, like I was saying before, s, because it's governed by the two exponential coordinates, is ranging from the lower bound is when s is equal to -1, and the upper bound is when s is equal to 0. And those curves are curves of like constant s, so it's this producing this rectangular thing that we aren't going to worry about a dependence that we might have in general on what the value t had. And then the t bounds were from 1 to 4. And so here our integral from 1 to 4, from -1 to 0, ds dt, is going to be the integral of our rectangular region of just the differential area. So we're just going to pick out the area of the region. Here the t width is 3 and the s height is 1, and so this region is going to have area 3 in the st world, which is saying that our function's integral in xy is just going to be 3. Make that clearly positive 3 here. Right. For another problem, and this one given to us in sort of the usual way, where x and y are just written explicitly in terms of these new coordinates. We have this integral over this sort of rather complex-looking region, where the x-bound is given in terms of these two functions of y, of a particularly horrid-looking integrand, sine of pi square root x plus 2y, all over square root of x squared minus 4y squared. And what we want to do here is use this change of variables that has been given to us, is going to be very simplifying. It's going to turn both the region into a somewhat simpler region, and very crucially is going to make the integrand a much more reasonable object, because actually performing this integral as written is sort of, these are functions that don't have simple integral or antiderivatives. So first off, let me sketch it, and I'll sketch it over here in the problem box. That in terms of x, y, our region, we have y ranging from 0 to 1, and then the lower bound on x is twice y, or actually I think there's a typo here. Well, not really a typo, but that there's this bound on x of twice y, and so we get out to 2 here, and then there's also this bound of 1 plus y squared. Oh no, this is coming in with a positive sign. Yeah, that's true. It's the lower x bound, which is the left bound. Yeah, I was worried about the lower bound in y. But yeah, no. It would have been just a overall factor of -1 if it were reversed from the way it is. But no. We've got our left bound is 2y, and our right bound is 1 plus y squared. And so our region is this almost triangular, but it's thinning as it goes out to reach this sort of cusp point at 2, 1. So our first task here is to figure out what the region D star looks like in terms of UV. The UV coordinates, and here I've given a description of it and a hint that it's this sort of just triangular region in U and V. But I do want to talk a little bit about how we could see that, and so what we sort of want to think of is we want to think about parameters U and V giving us access to these 3 boundary curves. So we've got the curve y equals 2x, the curve y equals 2x, the curve x equals 1 plus y squared, and the curve defined by y equals 0. And with these 3 curves, y equals 2x, 1 plus y, x equals 1 plus y squared, and y equals 0, we want to think about curves in UV that are going to give us the same thing. And so here, it's a little bit of guesswork can go a long ways. And so our curve y equals 0 is going to be this curve where UV equals 0, and so we might as well pick one of them to be 0. It's going to be a curve where one of them is equal to 0, and we can see that because the terms for x and for y are sort of symmetric in UV, that we could exchange u and v and aren't going to change the values. that we know that our parameterization is going to like only involve one of them. And so here, the sort of the one I chose was for v to equal 0. But equally well, you could say it's the curve u equals 0. But that constraint is going to ensure that you get y equals 0 and are allowed to change x. That x is going to then be determined by just u squared, and so you're going to get 0 less than or equal to u less than or equal to 1 is going to be parameterizing this part of the curve that's going from 0 to 1, and that'll like define one of your boundaries. Then this curve x equals 1 plus y squared is, admittedly going to be much harder to work with. But if we sort of like look at this point that it starts with was going to be the point corresponding to u equals 1, and so we could I guess we can see that like the x coordinate at the beginning is going to be, well, 1 plus 0 squared, I guess, but 1 plus v squared evaluated where it is, and if u stays at 1, then the second coordinate is going to be v, and so it's a bit of a stretch to see this immediately, but like hopefully at least in convincing yourself it's true, it feels somewhat comfortable that like by enforcing u to equal 1, that's going to enforce x to be 1 plus v squared and y to be v, and so x would be 1 plus y squared, and there you want y to range from 0 to 1, and so v would be ranging from 0 to 1, would be describing that piece of curve, and then the final one, y equals 2x, we can see that if u and v are equal, and again they're ranging between 0 and 1, then the x coordinate is u squared plus v squared. It's the same thing, so 2v squared, and u times v is just the same as 1 factor of v squared, and so we get again the same thing that oh goodness, sorry, this curve was y equals 1/2 x. U and v result in x being twice y. Yeah, sorry, it's 2y, not 2x there. I was wondering why this looked wrong. Okay, and so what these tell us is that we're bounded by the curves v equals 0, u equals 1, and u equals v, which is in the sort of uv space, picking out this triangle that goes up to height 1 in both coordinates. Although, like I said, equally well, you could choose, instead of the triangle that's below that line, is the triangle to the left of that line, if you were to break the symmetry in the other way and say that it's determined by u equals 0 and v equals 1. But once we've made one of these choices, we can start computing our area element. And so here we want to take this matrix df of x and y in terms of u and v. And so x is derivatives for u is 2u and for v is 2v. V's derivatives, we get a v for the u derivative and a u for the v derivative. And so our area element is going to be the absolute value of 2u squared minus 2v squared. Is going to be twice absolute value of, well, twice the absolute value of u squared minus v squared. But in this triangle that we're sort of working in, we know that v is less than u, so v squared is going to be less than u squared. And so our expression, it's probably good to leave it in terms of absolute value here, but to sort of convince ourselves that it is you know, a nice smooth function or something. It's a little bit pleasant to realize that we're only using one sign of the absolute value. Alright, now the last step is to figure out, well, the last step before doing our computations is to figure out what these functions look like. In the integrand, the sign of pi times the square root of x plus 2y and the reciprocal square root of x squared minus 4y squared. And so here we're just sort of substituting in what we know x and y to be in terms of u and v. And so we know that sorry, that's just x, not x squared. We know that x is u squared plus v squared, and y is uv. And so cordon that off a little bit. We know that this x plus 2y is going to be an x squared plus 2uv plus v squared, which is going to be a u plus v quantity squared. And so we've got sine of pi times the square root of the square of u plus v. And again, in the region that we're interested in, u and v are both positive, and so that square root is going to be well defined as going to be the positive square root. And so we just, the square root of the square is the thing itself if it's positive. And similarly, the denominator here, x squared is, well, this one I'll write out in two steps because it's a little bit more complicated. X squared is u squared plus v squared squared, and so we get a u to the fourth plus 2 u squared v squared plus v to the fourth, and then we're subtracting off 4 times uv squared, so 4 u squared v squared onto the square root. And here we can see that we've ultimately got u to the fourth plus minus 2 u squared v squared plus v to the fourth, which we can recognize as u squared minus v squared squared. And so again, we're taking the square root of something that we know to be a square, and the way I said it, u squared minus v squared is the sort of the positive version of that. And so our function is sine of pi u plus v over the square of u squared minus v squared, or so just u squared minus v squared. And so here again we see that as in the previous problem, and I suppose I've perhaps overrepresented how often this happens. It's not always going to be the case, but we've got something in our function that cancels out with the extra factor from our volume element. And so the actual integral that we want to do, double integral over this region D of, I will just write it as f of xy, this initial function that we had, dx dy, is really going to be just the integral from 0 to 1 in u times the integral from 0 to u in v of sine of pi u plus v dv du. And here I have not left myself enough space for this, so I will erase this computation at the beginning. But this integral is, already we can see, sort of a very friendly thing. It's just a sine function that's got these two things in the argument, but they're both coming in linearly. Let's see if we need. So we will sort of teleport up to the top of the board here. That we can take just first the antiderivative. Oh, I forgot. There's a factor of 2 in the volume element, which I unfortunately just erased. But it was 2 u squared minus v squared. We only divided by u squared minus v squared, so we've got a factor of 2 left over from that Jacobian determinant. And so we've got our factor of 2. The antiderivative of sine of pi times u plus v with respect to v is going to give us a factor of 1 over pi, and the antiderivative of sine is minus cosine. So I guess we get a negative sign. Integral from 0 to 1. And then we've got cosine. When we evaluate at u, we've got sine of pi u plus u, and so cosine of 2 pi u. And then minus when we evaluate at 0, we just get cosine of pi u du. And then if we take the antiderivative again, we're going to get 2 over pi squared with another factor of pi coming out of both of these. The cosine of 2 pi would give us another factor and would give us a sine of 2 pi u, and then the cosine itself of just pi u would give us sine of pi u. Those are evaluated from 0 to 1, but we can see that we're going to get sine of 2 pi, sine of 0, and sine of pi, and all of those are 0. And so every term in that vanishes, and we can see that our initial integral that we cared about, that we would have sort of very little hope of doing directly in terms of x and y, just turns out to be 0. And if you play around on like a graphing calculator or something, you can see that the curve, I don't think it's quite straight, but the curve on which that function crosses 0 in this region is like kind of halfway in it. So it does kind of make sense that it's going to be balanced. But there would be like very little hope of even making like geometric arguments based on the nature of the function that would have to happen. But with this change of variables, we can turn it into just a simple trigonometric computation. One final thing before I switch over to a new recording for the three-dimensional coordinate systems, which be sure to check for that, is the sort of most classical change of coordinates in two variables, which is polar coordinates. And so here, instead of talking about the usual Cartesian coordinates x and y, we deal with everything in terms of the radius away from the origin, r, and the angle up from the x-axis, theta. And so this is given by the sort of usual parameterization. X is r cosine theta and y is r sine theta. Although here we're thinking about r as something that can vary as well, rather than just a parameterization of a single circle. And if you work out the area element with this using the change of variables formula from above, that area element will be just r times dr d theta, or of course r d theta dr. And it's important to keep in mind just that we've got these restrictions here that we're measuring r always as a non-negative number and theta always between 0 and 2 pi. And here's where we sort of invoke the sort of lower dimensional behavior, not causing problems, because of course if you've got points at 0 radius with different angles, it'll map to the same point. And likewise, if you've got points at the same radius with angles differing only by a factor of 2 pi, they'll be mapped to the same point. And so here, just 0 and 2 pi. But that's not actually going to cause a problem for us unless somehow we've written down functions that are supposed to take on different values there. So it's good to check that our functions are all appropriately periodic and make sense with positive radius. And so a problem here is to compute the volume of this region that's bounded below by what we can recognize as the radius itself, and bounded above by this expression that we can see is going to be 1 plus sort of hemisphere of radius 1. And so if we were to sort of draw this out in a three-dimensional picture of x, y, and z, we get a cone whose width is proportional to the radius, and on top of that cone, we've got this hemisphere. That's the half of the sphere centered on 0, 0, 1 of radius 1. And we can see that these intersect. The sphere centered on 0, 0, 1 of radius 1 is going to meet when z equals 1 is going to meet the the cone of radius 1 away from like the z-axis. And so these all intersect, it creates something that looks kind of like an ice cream cone, which is why I called it that. And so here, if we were to write down the integral from last time of the sort of upper height minus lower height that's computing this, oh, I guess we're not integrating over c, we'd be integrating over let's call it d, the sort of the disk of radius 1. We'd be integrating the upper height, 1 plus the square root of 1 minus x squared minus y squared. And minus the lower height, square root of x squared plus y squared. And this whole thing integrated in x and y. If we convert to polar coordinates in this disk D of radius 1 that we're lying over, we see that we've got this integral where the radius in the disk is going from 0 to 1, and the angle goes all the way around the disk from 0 to 2 pi, because we're taking this full around the full circle. And then we here have to reinterpret our function in terms of r and theta. And so hopefully, x and y only come in as x squared plus y squared, which is r squared. And so our function is 1 plus the square root of 1 minus r squared minus the square root of r squared, so r. Here we've got our factor of r from the Jacobian determinant, the sort of area element. And as written, it's d theta dr, but we can exchange the order of r and theta in that element. And so this, we want to integrate. We don't have any dependence on theta, so that integral just treats it as a constant. We get a factor of 2 pi over all. And then I'll actually even just, well, no, I'll write this out. That we then have 0 to 1 of 1 minus, multiplying in this r, we get an r minus r squared plus r times the square root of 1 minus r squared dr. And so the first two terms are very easy to anti-differentiate. They're going to get a 1/2 r squared minus a 1/3 r cubed from 0 to 1. And then for this last term, we can, looks like it's going to be, small. We can use this substitution. U is 1 minus r squared, which would give us that du is minus 2r dr, to see that what we've got here is a square root of u times minus 1/2 du is going to be integrated, and then when we plug in the bounds, we plug in 0 to 1 minus r squared, we get a 1, and if we plug in a 1 for r, we get a 0. And so we may as well take out the minus sign and switch the bounds to the usual order by using the fact that the integral the wrong way around is minus the integral in increasing order. And so that term there means that we're going to get also a 2 pi times times 1/2 times 2/3, so I'll just write that as 1/3 u to the 3/2 between 0 and 1. And so if we evaluate these at 0, we get 0 in all cases. If we evaluate in 1, half r squared is a half, minus a third r cubed is 1, a third u to the 3/2 is 1/3, and so we're getting 2 pi times 1/2 minus 1/3 plus 1/3, and so it's going to give us just a ultimate value of pi for this integral. Okay, so here I will end this video. So be sure to check out the week 9 video 2, which will be on change variables in terms of triple integrals.